now we'd like to find the electric potential inside the surface of our spherical insulator. So B was a point outside, A was a point at infinity, C is on the surface. We'll take D to be at some point inside the insulator. So there's the radius D. So we'll begin with our expression for the electric potential. This time we're trying to find the potential inside, which means we have R less than the radius of the sphere. So our electric potential is delta V, is the difference between two potentials. Let's take our difference to be between C and D. So let's find the potential as we go from C to D. So our final will be point D, our initial will be point C. Makes sense to take this as a reference point because we know what the potential is at point C. So that's equal to minus the integral of the electric field times dr. Here we've just skipped straight to the step from E dot ds is the same as ER times dr. And this is the electric field inside the insulator. We're going over the limits of our integral, where the distance at C is the radius of the sphere. The distance at D we'll just call RD for right now. So we've got the integral of E times dr. Let's put in the expression we know for the electric field inside an insulator, and we covered that in chapter 24. So the electric field inside of an insulator is K times the net charge times the distance you are from the center divided by R cubed, and that's integrated with respect to R. And this was a result we got to from considering Gauss's law. We knew that the integral of E dot dA was the charge enclosed over epsilon naught. We had to find the charge enclosed by thinking about the fraction of the volume that was enclosed and how much charge was inside that volume. So that was what we did to find that part. So there's our expression for electric field. Let's take our constants outside the integral. So minus K times Q over R cubed. Those guys are constants. Then we've got the integral from the radius to that distance D times R dr. R dr, that's an easy one to integrate. That's going to be R squared over 2. We're going to evaluate that at our limits of RD and the radius, so let's fill those things in. Come down to this line, so we have minus K times Q over R cubed times RD squared over 2 minus the radius squared over 2. So there's our expression right now. Just like we did before when we found our potential at point B, instead of writing RB, we just wrote R. Let's do that again. So let's just write plain R here instead of RD. So we just know we're talking about some general distance inside the sphere. So we're doing pretty well now. This is our expression for the change in potential as we go from point C to point D. Let's just solve it for the potential at point D. So VD minus VC is the same as the potential at D minus the potential at C. We found that in the previous video to be KQ over R, so let's fill that part in. And that equals this expression. Let's bring our KQ over R to the other side to solve for VD. Okay, if you left your expression here, that wouldn't be the end of the world. We can simplify it to get a slightly nicer expression. And the value for doing that is it'll make it a little bit easier for us to do a plot of the electric potential if we wanted to. So let's just do some algebra and simplify this a little bit. Step number 1, let's just take KQ over R outside of the whole thing. So KQ over R outside of minus 1 over R cubed, 1 over R squared. When I take my KQ over R outside of this thing, I'll get R squared left, times R squared over 2 minus R squared over 2 plus 1. So that's the first step in the algebra. Now what I can do is I can multiply this R squared inside these terms right here. get minus r squared over 2 times the radius squared. Minus times minus gives us a plus. I get r squared on top, 2r squared on bottom. Those r squareds we notice will just cancel right out there. Then I've got my plus 1 here. So let's simplify this even a little bit further. Why don't we just rewrite it first so it's a little bit more obvious what we're doing. So 1 over 2 plus 1 is going to give us 3 over 2. And now if we wish, we can take our 2 outside. So we get k times q over 2 times r, side of 3 minus r squared over r squared. So there's an expression for our electric potential inside of an insulating sphere.